All right. Once this decides to load up. Come on. Is it going to turn on? There we go. All right, everyone. Welcome back. As I was mentioning before class, there was a water leak in the building over break, and one of the things it led to was some haywire with the HVAC. So if there are certain pockets of the building that seem a little colder than normal, that's why. But I hope everybody had a relaxing and wonderful Thanksgiving break and are ready to put a pin on CE 312 because this is our last week, and we are going to finish this out with a bang. So let's go through a couple things. First off, let's go through some minor logistics, but I usually like for the Monday we come back to go through some sort of, hey, here it is logistics for the rest of the semester. So the attendance grades are up to date as of today. What I will probably do is collect the attendance grades for this week and just post them all at once. So for those of you playing the at-home game, if you're coming to class, your attendance grade will either stay where it is or go up. So I'll do that a little near the end of the week. All the outstanding homework is graded, other than what you turned in today. How did homework 8.5 go? Was that smooth, hopefully? Okay, good. I submitted or sent you the grade reports on Project Submittal 2, so you all have your final grade on the project, and it's been posted to Blackboard as well. Okay. Now I'm giving you homework 9.1 today, which is due Wednesday. But before we break from this, I want to go through some logistics to end out CE 312. Okay. So let's talk about some remaining housekeeping. And so by remaining housekeeping, I want to talk about what you need to worry about between now and the end, because I know you have other classes to worry about. You have projects and papers and lab reports and all that stuff, and I kind of want to just put a nice little bow on everything going on in here. So what about homework? Okay, so again, current grading status, everything outstanding is graded. Obviously 8.5 hasn't been graded because you just turned that in, but homework 8.5 is due today. What's left? Okay, so you have two more assignments. You have homework 9.1, which is on aids for structural analysis, and you'll understand what that means today. That's going to be due Wednesday. And then homework 9.2, which is on tributary area, that's going to be due on Friday. Now, I'm not accepting late work on homework 9.2 because I'm going to turn the solution on right when it's submitted. And the reason I'm doing that is because the final's coming up. So the solution's going to be uploaded right at 11 a.m. Okay? I do have one bonus assignment for you, and that is if you could do your course evals. I don't want to see what you wrote. I don't want to see what you said. You could say I'm the worst professor ever. But I do want you to take the time to do them. And if you do have any legitimate feedback on things that you'd like to see improved in future offerings, I do really appreciate that. If you upload a screen capture that shows that you did it, I will add 10 points to your homework average. Okay? And it's sort of like if you do the math, it equates to about an extra point on the end of your grade. So if you have an 83 in the class, it would mean you have about an 84. It's not quite that, but I round the grades anyway, so it's about that. I'm closing that, so the survey itself closes on Friday, but I have the screen capture uploaded until Tuesday, which is the day that we have the final. What I would suggest is that if you've done your course eval, please upload proof that you've done it. I don't know who's done what surveys. The only thing that I know is how many of you have done it. So like if everybody in the class does it, like if I have a 100% response rate, then I'll just give everybody the credit. But if not, if you do the survey but don't upload the proof, I'm not going to know that you did it. And there have been instances where I've had like 20 students do the survey, but only 18 upload the proof. So there's 2 of you out there that I don't know that you did it. So that's like, I mean, it's free real estate. So, take it. Free points. Okay. Let's talk about some other remaining housekeeping. Let's talk about lectures. So we're going to be doing structural analysis aids today. We're going to be doing tributary area on Wednesday. And these 2 lectures, if I wanted to give an overall theme, it's sort of bringing the class back to the real world. That's kind of what we're focused on this week. And then we have our exam review on Friday. Okay. Speaking of the exam is on Tuesday, December 5th. The time slot that we have been assigned is from 10:15 to 12:15, but do not think that that means I'm going to give you a 2-hour long exam. I'm not. This exam is going to be formatted just like all the others. I'm designing the exam to be 50 minutes long, but you're still getting the full 2 hours, okay? Just about every single time I offer this exam, an hour and a half in, most of you are already gone, okay? This is not intended to be a time crunch, and it is also not comprehensive, okay? What I'm covering on the exam is everything we're covering this week and influence lines. I am also probably going to ask you some conceptual questions about masthand, but you're not going to be running masthand on the exam. It's just some conceptual questions on it. But influence lines, masthand, and what we covered this week, that's the final, okay? I am also going to do a course learning outcome survey during the exam as well, just sort of the course outcomes on a 1 to 5 scale, but that's pretty straightforward. But that is this class in a nutshell. Done, okay? Anybody have any questions? And one thing I will reiterate, again, I do round. So if you have a 79.5, you get a B, okay? So when you play the at-home game, that spreadsheet is not figuring out what grade you need to get an 80. It's figuring out what grade you need to get a 79.5 or a 69.5 or an 89.5. So it's figured that into account, okay? Make sense? All right, any questions? All right, so that is the logistics for the class in a nutshell. Let's get into some topics, okay? And so I have 2 additional topics for discussion today. And like I said, they are focused around the real world, okay? And the first topic I want to discuss is what I call aids for structural analysis, or maybe a more specific way of phrasing it would be a formula set for common loading situations, okay? So what do I mean by aids for structural analysis? Okay, I want to refresh everybody's memories for a second, and I want to look at these 2 problems, okay? Now, it's been a while since you've done some structural analysis, unless you did the homework assignment about 20 minutes ago. But if you did your structural analysis assignment before break, then it's probably been a while since you've done this. But I want to look at these 2 problems, and I want to make the point that we have analyzed these problems this semester in class, okay? Whether we were focused on determining reactions or shear and moment diagrams or what have you, we've done these problems. Now, I want to be clear, I don't think that was a bad idea. I mean, these problems are kind of tough, okay? But what they've done is they've served a purpose from an educational perspective. I mean, my philosophy is that if you can analyze this, you can certainly analyze what you're going to do in the real world, okay? But they are what I would say unrepresentative of what I'll call bread and butter analyses. And what I mean by that is this isn't the type of structure that an engineer is going to see on the regular, on the daily basis. This is very abnormal from a day-to-day practicing engineer's perspective. Day-to-day, an engineer is going to see something like this. I'm just using this as an example. Just a cantilever beam with a distributed load, okay? So I make a point here. I've got 2 cantilevered beams here on the screen. This one is a cantilevered beam with a uniformly distributed load. And that one is a cantilevered beam with a uniformly distributed load. I argue that this is the same problem. These 2 are the same. The only difference is the numerical inputs. Instead of a length of 25 feet on the left, we have a length of 37 feet on the right. Instead of a load of 3 kips per foot, it's a load of 1.95 kips per foot. Instead of analyzing this problem over and over and over again, is there a way that we can derive some really nifty plug and chug formulas that will do this for us? So that instead of dealing with 100 different, cantilevered beams with uniformly distributed loads, why don't we just deal with one and deal with it over and over again symbolically, okay? That's what I mean when I say aids for structural analysis. So this is an example analysis aid, and we are going to derive these equations together later on. Okay, so so that you are aware, I imagine most of you are. How many of you are taking steel next semester? I'm just curious. Okay, so steel is very different than this class. I'm sure that some of you would agree this class has felt very theoretical. You know, it's a lot of applied physics and what have you. Steel is not that. It's very applied. There's a lot of very real-world discussions in there about threaded, bolts being subjected to shear and whether or not the threads are included or threads are excluded, or what is block shear and how do we handle, edge distances and bolt spacing when we're considering corrosion, like all sorts of real deal issues. But we do have to do some analysis. And the steel manual, as is the case with many code specifications, will provide design aids that look like this. This design aid actually comes from the American Wood Council. So this would be the one that you would get if you were looking at your timber spec. Okay? And so what we have here is an example analysis aid. This is AWC Design Aid 6. You all can Google this and download it right now for free. I mean, there's nothing stopping you from doing that. And there's a series of figures. So figure 12 is a cantilevered beam with a uniformly distributed load. And so here's the cantilevered beam. This is what the shear diagram looks like. This is what the moment diagram looks like. What's the vertical reaction? It's WL. So if I know the distributed load, I know the length, boom, there's the reaction. What about the maximum moment? What's this moment value right here? It's WL squared over 2. If I know the load and I know the length, WL squared over 2, bam, there's the moment. What about the maximum shear? Bam, there's the maximum shear. What about deflection? Where's the biggest deflection going to be? It's at the free end. How do I compute it? Bam, right here. What if I want the deflection at any point? Plug and chug, bam, right there. Okay? So no more having to analyze this problem over and over and over again. The analysis is done. Okay? And this is very useful when you're dealing with routine cases. I cannot tell you how many beams in this building are treated as simply supported beams with uniformly distributed loads. And if you can do that one problem, you can do it over and over again. In fact, when we do a beam design in steel, that's a lot of what we're going to focus on. It's pretty routine analyses. Now, these analysis aids are neutral in regards to units. Okay? So there's not going to be a unit conversion factor built into it. So whenever you're looking at, let's say, deflections, you either need to use a unit conversion factor, so like WL to the 4th over ADI times 1728, or you need to plug everything in a consistent unit system. Okay, I just mentioned that so that you're aware. Okay, sound good? Okay, so this is one from the wood specification. This is one from the steel specification. Okay, this is from the steel manual. Well, for those of you that are taking steel, you'll end up buying one of these steel manuals, and we'll actually use aids like this in the class. There are a couple things you need to be careful of when using the analysis aids. Okay, so for example, this is the one for a simply supported beam subjected to a triangular load. And one of the things you need to be careful about is the inputs. Okay, so for example, if you look at the reaction is W over 3. Well, the question is, what's W? Well, W is 2.5, right? Wrong. It's not. In this case, what W is referring to is the total amount of load that's on the beam. So for this analysis aid, W isn't 2.5, it's the area of this triangle, 1/2 of 2.5 times 40 or 50 kips. Okay? So if you plugged in 2.5 into these values of W, you get the wrong answer. It's not because there's anything wrong with the aid, it's because the aid is treating W as something differently. So you do need to be a little bit careful when you use them. And one way that you can suss out what's going on is to look at the units. For example, this R1, this reaction right here, is W over 3. Well, if you take this and divide it by 3, you're going to get kips per foot, but the reaction is supposed to be in kips. So that should tell you something's wrong. Okay? Does that make sense? Okay. Another thing that you need to watch out for is whenever you're using multiple aids. So let's take a look at this problem right here. So this is a simply supported beam, and I've got a uniformly distributed load of 1.3 kips per foot plus I also have a 17 kip a 17 kip concentrated load right here. Okay. Now I propose what I can do is I can say that that equals this beam plus this beam. Okay. So you see what I did? I'm just treating each load separately. But here's the problem. Okay. So let's take the first beam. So here's the first beam, a simply supported beam with a uniformly distributed load, and I can calculate the maximum moment. Okay. Now the maximum moment is the biggest value on the moment diagram. Now for this beam, that's going to be right smack dab in the middle, right? Okay. But on this beam, it's not in the middle. Okay. For this beam, the maximum moment is where the load is. So sometimes when you're using these aids, you're tempted to say, oh, well, the maximum moment is that plus that. That's wrong. Okay. That's wrong because those two values don't occur at the same location. So you can't add those Mmax terms together because they don't align with a similar location on this beam. Okay? But what you could do is instead of adding the Mmaxes, you can add the moment functions together. Okay? Probably what I would do is if I was doing this problem, I would handle it one of two ways. I would probably add up the functions in Excel and plot it, or honestly, I might just analyze the structure myself without these aids. These aids are intended to be shortcuts for simple situations. But if the problem gets too involved, the question is, do I really want to break out all these, odd formulas, or do I want to just do the problem? I mean, one of the things about all the methods that we've been discussing this semester is that they work great for problems like this. This would be a really bad problem to use analysis aids on because, for one, I don't think you would find any analysis aids for a problem like this. But even if you did, the math would get so cumbersome that you might as well just analyze the problem directly anyways. Okay? Does that make sense? So in order to understand them, I want to derive them. So I'm going to go through the process of deriving the analysis aids for this problem. Okay? So let's see where we get with this. Okay? So we're going to derive the analysis aids for this beam, okay? Now, let's sort of take stock of what we would want, okay? If I'm an engineer, what do I want to know about this beam from an analysis and design standpoint? Well, okay, so let's start off with the reactions, okay? So reactions. Now, I'm asking for RV and RM. What that means is that I have a beam like this, and I've got this distributed load on it. I'm going to have a vertical reaction RV and a moment reaction RM. I'm going to see if I can derive formulas for that. Okay? What else do I want? Well, what do I got here? I've got shears. Okay? So what do I mean by shears? Well, I've got here Vx and I've got Vmax. What do I mean? What do I mean by that? Well, let's see. If I were to draw the shear and moment diagram, let's just draw the shear diagram. What would the shear diagram look like for this beam? I have a constant load over a beam of length L. So what would the shear diagram look like? Just conceptually. Constant load means the shear diagram takes what shape? Is it quadratic? You're shaking your head no. What is it?
Triangular?
It's a line. It's a linear load. So the shear diagram will probably go something like this, and this will hit RV, or negative RV, and jump back up to 0, right? So actually what we could do right now is we could say that Vmax is going to be whatever RV is. Make sense? But we don't know what the function is. Okay? Now, let's take it one step further. What does the moment function look like? So help me out. What do you think the moment function is going to look like? Is first off the shape. If this is linear, what's this? Quadratic, okay? So we're going to start at 0, and so are we going to go 1 or 2? 2. It's because I did this. Hold on. A little to a lot. A little to a lot, right? A little value to a lot of value, little slope to a lot of slope. The moment diagram looks like that. And what are we going to get down to? RM, then back up to 0. Right? So already, on the moment side, we don't know what m of x is, but we do know that m max is Rm. Now we're missing one thing here, and I'll move it over here because I don't want to squanch, is deflections. So what we're going to see is if we can figure out delta max, we're going to see if we can figure out delta of x. And that it depends on whether or not we have time. So let's see what we can see. Now what we're going to do is we're going to handle this problem the way that we've handled every problem this semester. We're just going to do it symbolically. That's the only thing that's going to be different. Okay? So let's start off with our reactions. Let's start off with reactions. Okay. So I've got W, and then this is L. So just redrawing what I put up here on the board. Okay. So remember, I don't like dealing with distributed loads. I will collapse that into a single point load. Okay. What is the magnitude of that point load? Exactly right. It's WL, right? Because if this was 2 kips per foot over a beam of 30 feet, you'd say the load was 60 kips because you did the load times the length. So this is WL. And what is this distance? There you go. Right? So what do we got? Well, let's sum forces. So we've got, what do we have? We have RV going up, and we have WL going down. So we have that. So maybe I'll put that right here. So RV is WL going down. Sorry, why did I say going down? That's going up. That's going up. I need to go up. Okay. All right, so let's sum moments. Now what I'm going to do is I'm going to sum moments at the support. All right. So if I sum moments at the support, do I need to consider RV? No. Do I need to consider RM? Yes. Does it belong on the left or the right? I think it belongs on the left, right? So we've got RM. And what do we put over here on the right? What goes inside here? WL times L over 2. So RM is positive what? There you go. All right. So this is WL squared over 2. And I'm going to put the sign or the directions right here, although that is not conventional in most analysis aids, because what will happen is over here you see the direction, right? So the RV is up and then the magnitude is right here. So typically this isn't put there. So maybe I'll go ahead and erase it. Okay? Now, let's see what we can figure out. Now, I'm going to recopy these shear and moment diagrams right here. So I'm just going to recopy this from the board. But you know what? Let's take a look at this shear diagram just a little bit. Okay, so we start at 0. We go down to negative WL and then back up to 0. What is the slope of that line? What's the slope of this?
Negative W.
Exactly right, negative W. The slope of the shear diagram is equal to the magnitude of the load. How about this? What is the area under the shear diagram? What's the area of that shear diagram?
WL squared over 2.
Exactly. Bless you. 1/2 base times height, or I guess I should say negative, which is, right? Is that right? So here's our moment diagram. Start at 0, go down to a negative WL squared over 2, and then back up to 0. Because that's what our moment reaction does. Okay, all right. Now, so this, okay, so we've already got a couple things figured out right here. So we know this is, WL. We know this is WL squared over 2. But we have yet to figure out the shear and moment functions. And we've already done this, though. We've done this in this class before. Whenever you want to define functions, we need to cut a section. So we're going to cut a section through an arbitrary point in the structure, and we're going to look left, right? Now, does it make sense to look left? Which would be easier, looking left or looking right? Looking left. Looking left, all we've got is the load. Looking right, we've got the load and all these reactions. Do it the easiest way, okay? So let's do this over here. So we'll say let me lower that down a little bit. All right. So this is W. Okay. What we're going to do is we're going to put a shear here. Now, positive shear, should I draw it down or up? Down. And moment. All right. Should it be clockwise or counterclockwise? What's positive? Counterclockwise. Okay, good. Let's make sure everybody's awake. All right. So, and this distance here is x. So collapse this again into a point load where this is Wx, and this moment arm is x over 2. So can anybody guess what our moment functions are going to be, our moment shear functions are going to be? I mean, how different is this from just this? It's really not all that different, right? I mean, what is this going to be? What is Vx going to be? Wx, okay? And this is going to be Wx squared over 2, exactly right. Now, there is the matter of signs to consider, so we're going to check that, but let's go ahead and do that. Because I think we might have an issue with those being negative, but let's just see. So going down, we have Wx, but we have V going down as well, right? So 0 equals V plus Wx, therefore V is that. So maybe I should have a negative right here. But I mean, I think that makes sense because what's the slope of this line? Negative W, right? So that should be negative. And if that's negative, I have a feeling that one's going to be negative too. Let's just verify. So what do we have? We've got Wx times x over 2, and then also m. Okay. Interesting. Now, let me ask you a question. Okay? Is there some independent way or some means that I have to verify whether or not those are right? Is there something you notice about these two functions? How about this? What is the derivative of that? It's that. Remember that the derivative of this needs to always equal that, okay? And so that should be something that you should be able to verify at the very end, okay? So if you independently derive your moment and shear functions, you should be able to differentiate the moment function and get the shear function, okay? Now, if you integrate this, you'll get that, but plus c, which is why it's easier to differentiate the moment function than it is to integrate the shear one. So, maybe I'll put the box around that. Okay. Not too bad, right? Okay. Does anybody have any questions about this so far? We haven't done this yet, though, have we? How do we do this? How do we determine deflections? Remember that? Remember the method of virtual work? So how does the method of virtual work operate? We have a real structure, but then we have a virtual structure. Somebody describe what the virtual structure would look like. How about this? What would the virtual structure look like if I'm trying to define delta max? What would the virtual structure look like? At the very end. And what other loads on the beam for the virtual structure? Some semi-trick question. Nothing, right? The virtual structure has all the original loads removed and just a single unit load where we're interested in finding deflections. See, for this right here, we already have that. What we now need to find is that. Make sense? So this is what we need to find. So how do we do that? First off, does everybody have all this on the screen? Do you need me to stay here? Okay. All right. Let's do it like this. So maximum deflection, okay? So what we're going to have is a real structure, which is going to look like this. And we found that m of x is that. But then for our virtual structure, it's that. Okay? Now maybe I should put my dimensions on here. Okay? So how am I going to find the virtual moment function? Tell me what to do. I mean, how do we find the real moment function? We cut a section. So how do I find my virtual moment function? Cut another section, right? So I'm going to cut a section right here. Bless you. And then we've got our little shear and our little moment, right? So I'm cutting a section right here, looking left, looking in the same direction that I did when I evaluated my real structure. And so if I sum moments at the cut, so what do I have? I have the moment going this way, but I've got 1 times x also going this way. Okay. I think my marker's dying on me. We'll use this one. So now we have our real function and our virtual function. Okay? I'm going to rearrange this screen a little bit because I don't want to scroll too much on this. So bear with me. We'll move this over here. And we'll move this over here. This you cannot do on a whiteboard, I must say. Kind of nice. Okay. So we have our real structure and we have our virtual structure. So therefore, delta max is the following. Right? Now, unfortunately, we've got to deal with a little bit of Calc 1. I'm sorry. We've got to deal with some Calc 1. But it's not bad. It's not that bad. So here's what I'm going to do. I'm going to say, let's pull out that fraction. There's little m. There's big M. Okay? See what I did? Just substituted. All right. Now, let's see what else we can do. I'm a big fan of whenever we're doing integrals, I like to pull all the constants out. I don't like constants inside the integral because I think that messes things up. So see how I've got a 2 on the bottom? Got a 2 on the bottom, and we'll put that right here. Is W a constant? Yeah, anything that's not X is a constant. So I'm going to pull out the W and the 2, and then I'm left with just that. That's pretty easy, isn't it? What is the integral of x to the third for those of you that have had calculus 1? Which is everybody. I was like, I know you all know this. I know you do. The integral of x to the third is x to the fourth over 4. So and we evaluate that using the fundamental theorem of calculus by plugging in the top number minus plugging in the bottom number. Again, I got one of those constants. I don't like dealing with constants. So W over 8 EI plug in the top number minus plug in the bottom number, and I get that the maximum deflection is that. So this is okay. Let's check something. I told you that we were going to be deriving an example that I gave you. Well, here's what I gave you. Let's see. How did we do? Let's see, WL. There's that. What about the shear function? So this V sub x, that's the shear function. What's that? WX. We had minus WX, but we're tracking the signs probably a little more expeditiously than they are here because as a designer, you can usually suss out the signs yourself. All right. M max, WL squared over 2. What about the deflection? That was the hairy one. What are we at? WL to the fourth over 8 EI. WL to the fourth over 8 EI. Well, by golly gosh gee, look at that. It's like we're doing something. Now, I'm going to leave this one for you if you would like to do it on your own, but I'm going to give you a little bit of guidance on how you would do it. Because there does become a point when it just becomes like alphabet soup. So I'm going to do a little bit of it. I'm not going to do all of it, but I'm happy to do some of it. But I find that whenever you're trying to teach this stuff, like once you get to the point when it becomes alphabet soup, I think you all kind of follow along with what's going on. So let me show you how this works. Okay. So this is the maximum deflection. This is the deflection at any point. So how do you do that? Okay. So let me show you how I do it. Okay. This is how I do it. Okay. So first off, we know for the real structure we know that. Okay? Now, what about for the virtual structure? Okay. So the way that I like to do this is, and the way I think it's easier to track everything, is I like to introduce a new letter, okay? So what I'm going to do is I'm going to place a unit load at A, okay? And I'll say it's A from the free end. Okay, so what that looks like is I have a beam that looks like this, and I'm placing, instead of the deflection at the free end, I'm placing it somewhere right here. Okay, so we'll call this 1.0. Okay, so this, okay, you heard that too, right? Mm-hmm. Okay, what is that? I don't know. Okay, I just... I'm just going to keep going. All right. All right. I got sidetracked there. Okay. So this dimension here I'm going to call A, and this dimension here I'm going to call L minus A. Okay? And there it goes again. All right, so now let's analyze the structure and let's see what we get. So if I have 1 down, then my reaction here is 1 up vertical. And my moment reaction, here's what my moment reaction is going to be. It's going to be like this, and the magnitude is going to be L minus A. Okay? So if I were to plot the shear diagram and the moment diagram, here's what they look like, okay? So the shear diagram, looks like this. So we start at 0, go to 0, drop down to -1, go over, -1, jump up to 0. That's what the shear diagram looks like. Is everybody okay with that? So the area under the shear diagram is going to be negative L minus A. And then the moment diagram is going to be 0, 0, and then it's going to drop like that, jump back up to 0. And this magnitude right here is going to be negative L minus A. Okay? And remember, the slope of this is -1. So what this is going to mean is that I'm going to have 2 virtual functions. I'm going to have an M1, which is 0, and that's valid from 0 to A, and an M2, which is going to be valid from A to L. Okay? Now the equation of that line, the equation of this line here, is actually really easy. It ends up just being A minus X. Okay? And if you're wondering how I got that, so I'm just using point slope formula. And what I'm going to do is I'm going to say that the coordinates of this point right here are A and A comma 0. So that's how I got that. So it's not really all that concerning. And then I know we're getting close on time, so I'll rush this last part along. So what we do is, in order to find the deflection at A, we say the integral from 0 to A plus the integral from A to L of this. And this first one goes to 0 because that first function's 0. And when you chug this out, this is where it just becomes alphabet soup, because we have the integral from a to L of once you chug this out, what you get is negative W over 2EI times, and I know I'm just giving you the answer, but this is when it becomes just alphabet soup. It becomes 1/3 AL cubed minus 1/4 L to the 4th minus 1/12 A to the 4th. And that's just after you do all this alphabet soup right here, which, I mean, because you've got to pull out the constants, you know, multiply it out, integrate it, all that. Once you do that, that's your answer. And, I mean, that's basically what they have here, just written in terms of X's instead of A's. Now, the only thing I'll mention to let you go, and I promise the problem on the homework is a lot easier. I've given you a homework assignment where you're going to do one of these. The one for the deflection is optional, and if you do it, that's 5 bonus homework points if you would like to. It's up to you. You don't have to. That's all I have. I'm going to pull the code up. We'll do tributary area on Wednesday.